about functions. So in talking about functions, we have only in Algebra 1 or pre-algebra talked about like the vertical line test. Remember way back we said if there is a vertical line that touches a graph more than one time, then it is not a function. So we're going to look at now more specifically, there are three different types of functions. There are functions that are called one-to-one, there are functions that are called onto, and there are functions that are both of those things. Okay, and that's what we're going to look at with these first three mappings. So if we look at a one-to-one function, all right, a one-to-one function, every domain are our x values. So every domain has its own range, which is the y values. So the definition for that, if we're putting it in math terms, each element of the domain pairs to exactly one unique element in the range. So what that would mean, I cannot have a 3 go to A and a 2 go to A. They cannot go to the same one. Okay? So we could kind of put that in, sorry, I'm now over to the side, in a little bit different terms, that no range value is repeated. No range value is repeated if it is one-to-one. Do you get that? Each one on the left is used only one on the right, 1-to-1. Now, we do notice that in a one-to-one function, you can have a range value that's not used at all. Okay? That C is not used by any of the domain values, and that's okay. It's just left out. That is allowed in a one-to-one function. If we look at an onto function, all the ranges are used. So each element of the range corresponds to an element of the domain. So what do we notice is different about this onto function compared to that one-to-one function? What do we notice that's different? Two of them are going to the same thing. Two of them are going to C, right? So here, ranges can be repeated. So ranges can repeat, but you cannot have leftovers. That's what it means here by all ranges are used. So in one-to-one, leftovers are fine. In onto, they are not. All right? So leftovers allowed, leftovers not allowed. And then if we talk about functions that are both of those things, each element of the domain pairs to exactly one element in the range. I meant to write that in a different color. Now, an all-encompassing rule for functions, and this is kind of part of that vertical line test that we talked about before, is no domains can repeat in a function. So this rule is true for all of the types of functions. So in order to be any of them, that means to go all the way over there to that. In order to be a function at all, we can't repeat the domains because then it would fail that vertical line test. All right, now, the example I use to talk about a function is a soda machine. Okay, what Coke machine, Pepsi, whatever you guys call it. I call it a soda machine. All right, so when you think about a one-to-one function, sorry, I couldn't come up with the word. Is the soda machine working? So these are the buttons. It's the input. I'm telling it what I want. This is the output. So where it's going to get its soda, like the sleeves of soda inside the machine, you know, like how it's in a big long stack. So here I pushed Diet Pepsi, and then it takes it from the Diet Pepsi sleeve. Okay, perfect. I get my soda. I push Starry, which is weird, but I push Starry, and I get Starry. I push Pepsi, I get Pepsi. There's Mountain Dew in there, but there's no button for it. So I don't know that there's Mountain Dew in it, so I'm okay with that. The machine is functioning properly, right? I push a button, I get what I want. Here, if we think of onto, I have, you know, Pepsi, Mountain Dew, Starry, and Diet Pepsi. This just means, or no, sorry, I said that wrong. I gotta look at what's in the machine first. In the machine, I have Pepsi, Mountain Dew, and Diet Pepsi. I just have two buttons that say Diet Pepsi. They both take from that one sleeve, but there's two buttons that say it. And this is just, there's one button and one sleeve of each one. Would you agree, and I'm gonna put this on the board, that if I had, I'm gonna write words this time instead. So if I had Pepsi, Mountain Dew, and Diet Pepsi, and then I had Pepsi, Mountain Dew, that if I had this, and we'll put Starry down here. Would you agree that that is not a properly functioning soda machine? Why is that not properly functioning?
Because you can get Mountain Dew or Diet Pepsi.
Right. Do you see how this domain is reused, right? And I said in order to be a function, in order to function properly, domains can't be reused. But here, when I push the Diet Pepsi button, I could get a Mountain Dew. It could take from that sleeve of sodas, or I could get a Diet Pepsi. Who knows what I might get? So this is not functioning. All of those, it's functioning fine. The first one's a little weird because we have one of the sodas they have in the machine, but they don't have a button for it. So it's weird, but it works. I'm not going to be surprised by what I get. Does that make sense? So that's how we tell the difference between these different types of functions. All right, so if we look at the examples down here. So functions can be given in different formats. The ones we looked up at the top are called mappings. This is called a mapping because we're mapping the domains onto the, well, I didn't mean to use the word onto, but we're mapping them with the ranges, okay? So if we look at example 1, if we want to list the domain, how do we list the domain? What are the domains again? We just list all of the x values. Okay, so if we look at the x values, remember our ordered pairs are x and y. The x values would be -6, -5, -3, -1, and 6. We do typically put them in order from least to greatest, and we need to put them in what's called set notation. Set notation just means you put the braces around them. Okay? So what would our range be? It'd be just all the y values. And again, it's typical to put those in order from least to greatest, which is not just straight across for this one. For the range, our lowest number is -9. Then we have a -7. Now, we do have two -9s, but we're not going to write it twice. You only write it that one time. So -9, -7, -1, and +7. And then over to the right, I'm just going to make that into a mapping. I know it looks like a chart, but we're going to look at the visual. So I'm going to list all my domains. And I'm going to list all my ranges. And then we're going to map them. So if we look at -6, what does -6 map to? If we look at that first ordered pair, -6 should map to what? -1. Then we should have -5 map to -9. -3 should map to -7. -1 should map to 7. And 6 should map to -9. So first question is this a function? Because no domain is reused. This is the only thing we can say is not a function if the domain is reused. So no domain is reused, so it is a function. That means it's either one-to-one, onto, or neither. Or I'm sorry, one-to-one, onto, or both. So which one is it? And why is it onto? Exactly. Two domains go to a single range. So this makes it onto. because of that -9, two values going to -9 on two functions can repeat the range. 1 to 1 cannot. 1 out, 1 in would be 1 to 1. Okay, let's look at the second one. So this one is given to us in chart form. What are our domains if we do from least to greatest? -2, -1, and 2. So I can go ahead and put those in the domain over here. What are our ranges? Okay. So we can do our mappings. +2 goes to -2. -1 goes to -1. -2 goes to 0. -1 goes to 1. And 2 goes to 2. First question, is it a function? Why is it not a function? Yeah. This is not a functioning soda machine, is it? -1 and 2. So you could either write not a function or you could just write neither because it's not 1 to 1 or onto. So this is the reason why, because of those. All right. I want you to look at these two. So the first one is a graph. So if I ask you for domain and range, isn't a graph really just a list of ordered pairs? It's just in graph form, so you can think of it that way to list your domain and range, and then tell me if it is a function, and then do the same thing with the mapping down at the bottom. When you have guided practice, I expect that you're probably going to talk to people. That's okay. All right, so it is not a time you have to be silent. You can talk about it. If you want to do it yourself first and then talk and say, hey, what did you get? That's fine also. So guided practice is I'm walking around checking to see if you guys get it. And then we talk about it. And it gives me a chance to yes. Yes. And I forgot to do attendance. Better do that. both of them. Yeah, go ahead and do both of them. Sorry.
Yeah, that's what I would. Say that.
I will say, no one has them both right, which is okay. That's why we do it. We're gonna go over them.
Did you see me?
I saw everybody's.
Are you sure?
I am sure. All right, let's take a look at the first one. So our domain is -3, -2, -1, 0, 1, 3, 4. I think most of you got all the domains and ranges right, though. Okay. And then our range is -3, -2, 1, 2, 4. Is it a function? Why not? Exactly. If we look right here, one of those is 2, 1, and one of those is 2, -2. So that is reused. The domain is used twice. So this is not a function. Okay. Domain and range here. Our domain is -3, -2, -1, 0, 1. And our range is 0, 2, 4, 6, 8. Everybody got this part wrong. It's neither. It is not a function, and I will show you why. How's it a trick? All right, here's why it's not a function. If a function is 1-to-1, then this would fail, or if this was 1-to-1, it would fail because of this, right? It can't be 1-to-1 because 6 has 2 different domains. So that leaves onto. Why can't it be onto? What's onto not allowed to have? An extra. Onto can't have, I don't know what that letter is. It's supposed to be an N. So it's not onto because it has an extra. Not 1-to-1 because 6 in the range is used twice. So if it's not 1-to-1 and it's not onto, it definitely can't be both, right? Because it's not either one of them. So not necessarily a trick question, but trying to apply both of those things, okay? All right, are we okay with 1-to-1 onto functions? Okay. Let's take a look at discrete and continuous. And I think this is a little more intuitive. Do you guys know what the word intuitive means? Intuitive kind of means common sense, okay? So when we talk about discrete functions are a set of individual points. They're all individual. They're dots, okay? And I know that barely fits in that little blank. And the graph of a discrete function will have points that are not connected. They cannot be connected. And then where it says line, cross out the word line and cross out the word A, because without the word line, then it just says usually a jagged, which is kind of weird. So they do not have to form a line. The dots don't have to form a line, okay? It can be random dots like different places. But they cannot be connected. So think about if we're talking about someone's shoe size, okay? And we have height versus shoe size. Height, you can have decimals and things like that. But shoe size, you could have a 0.5, but you're not going to have like somebody wears a 6.3257, right? It doesn't make sense. So it would be individual points on a graph that would not be connected. So a continuous function, on the other hand, the domain of the relation has an infinite number of elements, and the relation can be graphed with a line or a smooth curve. Now, if we look at this line, what tells us that it's infinite? The arrows. So you're going to have arrows on this if it is continuous, because it's going to continue to the left and right. The domain will always be infinite. That will come into play later when we talk about domain and range. The range is not always infinite. So in this case it is, because it's a line that goes up and down forever. But think about if we had a parabola that was going like this, it doesn't go forever downward, it just goes forever upward. Okay? So the range is not always infinite, the domain is. All right, so if we take a look at this example 2, graph is showing the length of the Tour de France in kilometers or kilometers each year from 2000 to 2009. Is this discrete or continuous? Discrete. It's just a bunch of dots. It would not make sense to be continuous. Because if we look at this by year, if this is the year 2000, and this represents 2001, I'm not going to have a point in between those. They didn't run the Tour de France from in the year 2000 and a half, right? That doesn't make sense. And so it has to be discrete. They measured it in 2000, then they stopped. then they measured it in 2001, then they stopped. So think about that. If does it even make sense to be in the middle? Now, is it a function? So since it's graphed, we really want to look at, does it pass that vertical line test? Does this pass the vertical line test? Yeah, there aren't any two that are stacked on top of each other. What would it mean if two were stacked on top of each other in this example? They measured it twice or ran the race twice in 1 year, right? So it would mean that in 2000, the race was one distance and another distance. Well, that wouldn't even make sense, right? Number one, they don't run the Tour de France twice in a year. It's only once a year. And number two, why would it be two different lengths in the same year, right? So it is a function. All right, the one down at the bottom, guided practice. What I want you to do to graph this, it's going to be from 2004. Oh, I don't want to write the 20 because it's not going to fit. So I'm just going to write 04, 05, 06, 07, 08, and 09. And then if you count by fives here, I think we can go 4. So you're going to graph these values, and they're in order. Okay, like the first one is 2004, etc. Okay, so go ahead and graph those. Decide if it is discrete or continuous, and does it represent a function? All right, so if we look at the graph, it would be like that. Do we think it's discrete or continuous? It is discrete. Is it a function? Yes. Okay. So, yes, at some point between 2004 and 2005, there was a change in how many employees this company had, but we can't assume that it is just a straight line between those. Because during that year, they could have gone up in employees and then back down. We don't know. They could have just gone straight from 25 to 28. So we can't assume that. So the data that we were given is discrete. We were only given the numbers that represent when they calculate it. Okay? So that is discrete data. All right. So On your practice, or not practice test, your pre-test, you had to graph a line. Now, I just kind of glanced when I picked them up. Most of you graphed the line just fine. Now we're going to look at graphing that line and then what does it mean for domain and range and all of that. So if we look at this, we know that we're going to start at -3 on the y-axis. And then our slope is 1/2. So we're going to go up 1 over 2. I'm going to do that a couple times just so that I can get my line to be straight. Since I don't have a straight edge up here. And I don't have any in there, sorry. I usually do, but I don't have any in the bins right now. All right, so we have a line. What's our domain? Remember what we said about lines a minute ago. What did we say about the domain of lines? It is the x, yes. It's infinite. So would you agree that if we're talking the x-axis, which is here, which goes left to right, that this is going to go on infinitely to the left and infinitely to the right? So we use the term all real numbers, and that is the symbol if you don't want to write out the words. It's 3 whole words. For all real numbers. So to write that symbol, if you want to use the symbol for the phrase all real numbers, you draw an 11 and then make it into a fancy R. That's how you do it. Okay? It's an 11 made into a fancy R. So anytime you have to write the phrase all real numbers now, you can just write a symbol. What about the range? Or a 1 and a fancy K. Yeah, that works too. What would be the range? So the range is talking about the y-axis, right? So what is this graph doing up and down?
Going up and down. That's a good one, Ricky.
Ellis, what'd you just say? Infinitely, yeah. It's the same thing. This is going up and down forever. Is that what you said, Brady?
I mean, I said it's going up and down.
Going up and down. I just wanted to add the word forever or infinitely.
Oh.
Okay, so if it's infinite, it is all real numbers. That's not a very good one, but that's okay. Is it a function? Yes. The only type of lines that are not functions are vertical lines. All other lines are functions. So if it's a line, as long as it's not vertical, it's a function. So what would this be? 1-to-1, onto, or both? It would be both. No ranges are repeated, no domains are repeated, and there's nothing left out. I don't have like some random y value without an x value. That would be weird. So this is a function, and all lines are also both. Okay. Is it discrete or continuous? Continuous. It is a line, so therefore it's connected. All right, I know the next one says guided practice. Normally you would do that on your own, but we're actually going to go through this one together because we haven't talked about parabolas yet. So when we talk about the domain, we said for continuous functions, right? Continuous means that it's a line or a smooth curve. Would you agree that's a smooth curve? It's a curve. What did we say about their domains? They're always what? Infinite, which means All real numbers. This graph, even though the arrows aren't drawn in, it's going to go forever to the left and to the right. Okay, if you picture your arms like starting here in a small parabola, and then they go out and out and out and out, it's going to continually get wider at the top. Okay, so that's going left and right when you talk about how wide something is. But what about the range? This one does not have an infinite range. Why not? Range is up and down. Does this go up and down forever? It only goes up. That means it has a starting point. If it only goes up, it had to start somewhere. Where did it start? At the bottom, which is at what number? I heard somebody say it. 1. So you agree this is y equals 1? Right there? So if it started at a y of 1, did it get larger than that or did it get smaller than that? It got larger. What symbol do we use to represent that something is larger? Greater than. Okay. Greater than. Could it be equal to 1? It can be equal to because there's a point there. So it's greater than or equal to 1. It'll always be equal to, I guess, unless there's some weird situation where you had a hole there, but I don't foresee that ever happening. I've not seen it happen before. Is it a function? It's a function. And 1 to 1, on to, or both? It is not both. It's on to. Do you see how these y's are going to be repeated? So it can't be 1 to 1 because the y's get repeated. Discrete or continuous? Continuous because it is a curve. It's connected. All right, the last part. Depending on who you had for 8th grade science, you've talked about independent and dependent. Have you guys seen that before? If you've seen it before, then you probably had Miss Johnson. She showed it, but that's okay. So here we have an x and a y axis. This is the x-axis. This is the y-axis. The independent variable is the x. Oh, I meant to put that in the... Okay, so that's our x. The dependent would be the y, and it's dependent because it depends on the x. So if I gave you a linear equation, y equals 3x plus 2, right? That's an equation in slope-intercept form. Wouldn't you agree that the value of y depends on what I put in for x? So the answer I'm going to get is going to depend on what I put in, what I plug in. So the input depends on the output. If we go back to our soda machine, doesn't what comes out of the machine depend on what button I push? So whatever button I put, well, this one's not a function, but we'll pretend that this line isn't there. So the soda I get depends on what button I push. This is independent. I have an independent choice, what I want. But this is the dependent. It depends on it. All right. Function notation to me is the easiest part. So I will probably go through this a little quicker. These two equations mean the exact same thing. We read this as f of x. Or you could say the function f in terms of x. Now, that's a lot of words. F, I want you to think about as just naming. It's just telling you which equation we're talking about. That F could be a G. Then it's the G equation. It could be an H. That means it's just the H equation. It's a way to signify which equation you're talking about if you have multiple equations. Okay? So, it could be F of X, G of X, H of X, T of X. It doesn't matter. And then X just means what variable are you using? So on the right side, there's an X. That's all that means. So if we look at example 4, f of x equals 2x squared minus 8. So we're calling the equation f. We're using x as our variable. So if I'm asking you to evaluate f of 6, what do you think I'm asking you to do? Put 6 in where the x is. I'm asking you take the function f and evaluate it for a value or an input of 6. So you're just going to take that equation, and everywhere we see an x, we're going to put a 6. Now, if this one only has 6 in one place, so therefore I'm only going to plug it into one place. If it had x in multiple places, I'd plug it in multiple places. So then if we are evaluating that, 6 squared is equal to what? 36. So then we have 2 times 36. I heard 72, that's correct. And then we have 72 minus 8. What's that give us? 64. So f of 6 is 64. Then I could say, okay, well, what's f of negative 2? And you would do back to the original, and you'd plug in negative 2 and tell me what that equaled. You're just plugging in the values that are given to you, okay? You've done that before. So if I said f of 2y, I'm going to take my equation back to the original, so to the f equation, and I'm going to plug in 2y. Well, what is 2y squared? 4y squared. So I have to square the 2, and I have to square the y. What's 2 times 4y squared? 8y squared. Can I combine 8y squared and 8? They are not like terms, so that is my answer. All right, on this last part, what will we do with the 2.8? Plug it in for x. So now we're talking about the g equation, which is right here. So I would plug that in for x. Now, instead of going through this one, I'm going to tell you that this one gives us negative 6.58. I'm going to have you get a calculator in a minute. If you cannot get to that, then I'm going to tell you, here are the mistakes people make when they plug it in. Number one, they forget the squared, or they don't plug it into both places and they just put negative 5 as the second term instead of negative 5 times 2.8. Okay, I'll give you a chance to get an equation get a calculator in just a minute. So on B, when you guys go to try B, are you going to get a single letter answer or a single number answer? No, because you've got a variable in there. If you plug something in with a variable, you're not going to get a constant as an answer. Okay, so if you want to use a handheld calculator, I have them in the back right below the pencil sharpener. You can grab that. I want you to try these two. Once you've done that, I'm going to give you guys an activity at your tables. Okay, so if you can move with somebody, okay? You're welcome to do it by yourself if you want, but I'd prefer if you could work with someone.
Miss Johnson's class are back.
What's that?
Miss Johnson's neighbors are back.
What
Yeah, Coach Daddy is back.
Oh. So if you do not get negative 6.58,
So we're even there.
it's S to D right here.
Now it's showing up for today. That one thing. What about you?
That sound, when you hear it, is her door. I was like, she's got. Is it your birthday today?
It's possible.
Huh?
It's possible. Oh, shoot. Thank you.
Sorry if you didn't want attention.
No, it's okay.
Are you 17? 17.
Very shooting. Listen to that.
Hit S to D. Yeah, these are different calculators probably than you've used before.
I'm still trying to think. Oh.
That makes it look a little more like what you're used to. Okay, good. You thought about it, didn't you? All right, you guys are ready to do this. So let me explain the activity because some of you guys are getting finished with the assignment, or not the assignment, with the notes. So you are going to get, I think it's 6, 2, 4, 7. Sorry, you're going to get 7, yes, 6, 7 of these little functions, or could be functions. They're actually relations. We don't know if they're functions or not. Okay, you're going to have them all face up, and then pick one of them. You're going to decide, do you think that this is a function, first of all? Then if it is a function, is it one-to-one, on-to, or both? Talk about it as a group, decide, and then flip it over, decide, and see if you're right. So they're like flashcards, okay? Go through all of them, and then if you got some wrong the first time, maybe put them back into a thing, try it again, okay? Does that make sense? All right. Here you go. All right, now I'm going to stop the video. And that is the answer to B, by the way.